All right, we are in chapter 14. We are looking at equilibrium, and this is our second video here. We have just looked at definition, saying that equilibrium is when the forward rate is equal to the reverse rate for a reaction. We're going to look at that a little bit more and bring back and figure out why do reactions reach an equilibrium in the first place. All right, so we're going to look at that. Let's move on to the next one. We're going to bring some stuff back from chapter 13. 13 was talking about kinetics, and we said that the kinetics, or the rate of a reaction, was dependent on the concentrations of the reactants. Now remember, it was the rate forward equals some constant K times the concentration of the reactants raised to some order. All right, now the order was based on the slow step of the mechanism, okay, and we had to do kinetic experiments to figure out what that was. And the K forward had to take into account the orientation factors and the activation energy of the reaction, okay? So that's our rate forward. Now, when we start a reaction, we assume we have a lot of reactants and no products, okay? So as the reaction takes place, your concentration of reactants is pretty high. So the rate forward, since it's dependent on the concentration of reactants, is also going to be faster initially. As the reaction goes, okay, you're going to start using up reactants to make the products, right? So what happens to the concentration of reactants? It will go down as your concentration of products goes up. All right, so if your concentration of reactants is going down, that will slow your rate. So look at these little clock type things that are measuring the speed of the reaction, I guess. And you can see the first one says the forward rate at the start is pretty fast. As you're starting to use up some of those reactants, it's going to slow down a little bit, okay, so then it's moderate. And then later in the reaction, as you've used up more, it's going to be fairly slow, okay, because you don't have as many concentration of reactants around. Reactants have to find each other. There's a lot of space between them. There's products kind of in the way now. So the rate's going to be slower on how you're making reactant to product. All right, that's good to understand. Let's look at the reverse reaction as well to get this understanding complete. All right, so the same thing can be said about the reverse reaction and its rate. So again, the rate of the reverse reaction will be equal to some K for the reverse times the concentration of the products, and they would be raised to some order as well. All right, and again, kinetic data can show you what that would be. So now the reverse is going products to reactants. Now initially, you will not have any products, right? If the reaction is starting with only reactants, and then over time reactants start turning into products. So initially you'll have a very slow reverse rate because you don't have any products, okay? And your rate of the reverse is related, okay, to the concentration of products. So if you have 0 products, you're not going to have a very fast rate. So the rate of the reverse reaction will start increasing as more products are made. More products are made as the reverse, or as the forward reaction starts going. All right, so here you go. This picture is a very good one to have a good understanding of what's going on at equilibrium. We talked about the forward reaction already on the previous slide. So initially, the rate of the forward reaction over time is going to be starting fairly high. And then we talked about how it becomes moderate, and then it starts slowing down as time goes on because you're using up some of the reactants, and so the concentration's gone down. We just said then that the rate of the backward or reverse reaction is going to start very small, okay, at 0, since we won't have any products initially, okay, and so as you start making more products, as the reverse reaction takes off, or the forward reaction takes off, you'll start getting more products. The rate of the reverse reaction starts speeding up until we've hit some time where we are now in an equilibrium state. And now you can see that the rates of the forward and the rates of the reverse are equal to each other, and this is what we call equilibrium. All right, so again, if you want to show these arrows, one way to know if a system's in equilibrium is to look at these little rate things and see that they're both pointing at the same spot. They're equal to each other. All right, that should be good for that. Let's just look a little bit at how we break this apart and we talk about this equilibrium constant. All right, so we can write an equilibrium constant for these reactions. Let me get this going. And this equilibrium constant will tell us where the equilibrium lies. Is it more for the product side or more for the reactant side? All right, we're going to bring in a little bit from previous chapter 13 again. Let's look right here. So for a one-step reaction, so a very simplified reaction, we know at equilibrium the forward rate equals the reverse rate. Now the rate forward is equal to the K forward times the concentrations of A. Okay, we're going to just say order of 1 here. And this equals the reverse rate reverse, which is K reverse times the concentration of B. Okay, so here our reaction was A to B. So as the concentration of B increases, okay, our rate will go. So when these are at equilibrium, we know that these rates are equal to each other. The rate of the forward equals the rate of the reverse. And we can then write it as K F forward times the concentration of A equals K reverse times the concentration of B. We're going to move this reaction or this equation around a little bit, and I want to get the K's on one side and the A and B's on the other side. So rewriting this, KF times concentration of A equals KR, concentration of B. I'm going to divide both sides by KR and both sides by A. What cancels out? KR cancels out on the right-hand side, and the concentration of A cancels out here. And so now we have KF over KR equals the concentration of B divided by the concentration of A. All right, and now this right here, KF over KR, we're going to call K equilibrium. Okay, we're just putting those two constants together and just calling them one constant. So the K of the forward reaction divided by the K of the reverse reaction, we're joining together, calling it just K equilibrium. And then what is this equal to? This is equal to the concentration of B over the concentration of A. Now let's look at what A and B stand for again. B stood for the product concentration, and A is the reactant concentration. All right, so this equilibrium constant tells us at equilibrium, does this reaction lie more to the product side or to the reactant side? Now, what value would K equilibrium have if it was more reactant side? We'll look at where the reactants are in the equation. They're B, right? So if it lies more to the product side, that means you have a higher concentration of B compared to A. So a big number divided by a smaller number, you would have a larger K equilibrium constant. All right, so the value of K equilibrium, if it is large, this tells us that the reaction lies to the right and it's product favored. All right, what happens if, and I'll just switch color just to make it a little easier, if you have a small equilibrium constant or expression? Small K EQ. All right, that means that your concentration of A is bigger than concentration of B. If you're getting a small value right here, that means that the thing on the denominator is going to be larger to make this a smaller value. A, again, stands for reactants. So if the reactant concentration is larger, you're going to have a small equilibrium constant. So small K equilibrium, the reaction lies to the left and is reactant favored. All right, this now is some important information. So you will now be able to write an equilibrium expression, and we'll look at that more in the next video here. And you're going to be able to look at when the forward and reverse rate are equal to each other, you can then calculate a K equilibrium. So there's two ways to solve for K equilibrium. One way is to know your concentrations of reactants and products at equilibrium. So if you know A and B at equilibrium, you can solve for K equilibrium. The other way is if you can use your information from chapter 13 and solve for K forward and K reverse at equilibrium, you can also solve for K equilibrium. All right, so we're going to stop there. We're going to look at writing these expressions and solving for K equilibrium a little bit more in the next video.